Hello everyone. This video I'm going to show you a torsionally statically indeterminate. Okay, and actually it's very similar to axial load in the section in section axial loading. In axial loading, we also have statically indeterminate problem in axial loading. And indeterminate, we have already talked about is in it's the indeterminate. It doesn't mean it cannot be solved. Okay, the indeterminate, that means you have to find a more equation by yourself. Okay, okay, here is a very similar description in axial loading. A torsional load shaft will be statically indeterminate if the moment equation of equilibrium is not adequate to determine the unknown torques. Okay, so for example, if there is and we apply a 500 newton meter torque on the section C. Okay, and the problem want you to solve the torque at A and B at the wall. Okay, if you just use here is the moment equation of equilibrium. Okay, because the whole system, the total, because everything is static. Okay, so the total moment of system must be zero. So we can assume the torque at these two ends is TA and TB. Okay, and okay, where's my pen? I'm sure. I'll call my pen. What? Okay. Okay, so if we apply this is 500 Newton meter, and it's counterclockwise, so it's 500. Okay, the whole system. Okay, so it assume the TA is yeah, it's clockwise. Okay, so let's say it's minus TA plus 500 minus TB. Yeah, it's clockwise, so it's negative. Okay, and equal to zero, and then we will see that TA plus TB is equal to 500. Okay, that means this is the moment equation of equilibrium, because the whole system, the torque must be zero. Okay, because everything is static. Okay, no translation, no rotation. Here we only consider rotation. Okay, and okay, so we only have this equation, but we have two unknowns, TA and TB. Okay, so we only have one equation, two unknown. It's not solvable. Okay, let's call statically indeterminate. Okay, if you using the moment equation of equilibrium, you got the equation, but you cannot solve it because you don't have enough. You need to find another equation to solve TA and TB. Okay, so this is called statically indeterminate. Okay. So here is a very simple demonstration of this to show you the concept of statically indeterminate in torque load members. Okay, here we use a very similar example. Okay, to show you okay how to solve this problem. Okay, okay, so yes, here is a steel shaft. Okay, showing here, and its diameter is 20 millimeter, and it's subject to torques here. Okay, indeterminate reaction fixed support on A and B. Yeah, very similar to the previous example, right? Okay, the demonstration example. Okay, and here is some procedure of a statical indeterminate problem, but actually this is almost the same as the section in actual loading. Okay, so if you already understand the statically indeterminate axial loading problem, so here you don't need to really to pay more attention on this, because it's almost the same. Okay, the conclusion is you need to find another equation by yourself. Okay. Okay, so here is the shaft fixed between the wall, and we apply two torque on section C and D. Okay, he said determine the reaction moment from A B from A, sorry, in AB. Okay, here. Okay, so this problem here it assumed the TA and TB clockwise, but not my habit. I personally like to assume everything is counterclockwise. Okay, because counterclockwise means positive, so I assume TB is counterclockwise here, and TA also counterclockwise here. Okay, and we can because the whole system is static. So TB, okay, and this it is counterclockwise. So plus 800 and this 500 is this counterclockwise and this clockwise, so it's minus 500, and this is TA is positive, auto zero. So TA plus TB, what do we get? It's minus 300. And here is the Newton. Unit is Newton. Okay, so we apply this the rigid body equilibrium only has two equations, but we have two unknowns and we have nothing else. So right now we cannot solve it, so we need to find another condition to solve it. Okay, so another condition is because this shaft is fixed between this A and B, between A and B. So what's the call it? And the twist angle is 0. The twist angle must be 0. Okay, because when we apply, so this shaft is fixed between the wall. Okay, and even with even with if apply the external torque on this member, but there will be a reaction torque from A and from the wall, and this torque will keep the whole system, and those doesn't have any deformation. Okay, so the overall 5BA is equal 5BA, that's the angle twist is equal to 0. And 5BA, because we have in this problem we have three sections. Okay, BC is a section, CD is a section, ADA is a section. So 5BA we can separate this 5BA in three different parts. 5BA just equal to 5BC. Okay, plus 5CD plus 5DA. Okay, so then and overall it's 0. Okay, overall there must be some summation, there must be 0. Okay, so this is another equation we can use. Okay, and for this equation, do remember what's the angle formula for angle twist? The formula angle twist is equal to TC over GJ. Okay, I think TC over GJ. Let's look at the previous PowerPoint. Okay. Oh, sorry, TL over GJ, TL over GJ, TL over GJ. That's the formula for the angle twist. I think we talked about this in the torsional loading. TL over GJ, TL over GJ. Okay, so TL over GJ. Okay, and so we have TB over LB. Okay, here we have two sets. So okay, so let's write down. Okay, what is 5BC? Okay, what is this sixth section? 5BC torsional angle twist in 5BC equal to T BC LBC GBC and JBC. Okay, and 5CD is equal to TCD LCD GCD and JCD, CD, and okay, final 5DA, so it's equal to TDA, LDA, GDA, and JDA. Okay, and these three add together must be 0 because the total also this doesn't have any twist. Okay, because this shape fix fixed by these two walls. Okay, there is no deformation. There's no deformation. Not so the angle of twist. And these three add together equal to 0. So these three add together is equal to 0. So these three add together is equal to 0. Okay, these three add together is equal to 0. And these three section, we already know this three section has the same area. Okay, same area. So that means it's JBC, JCD, and JDA is the same. So because these three add together, so we can divide these three terms, and also this is the same material. So these three must also be the same. Okay, so by this condition, by this another condition, we will have TBC times LBC plus TCD times LCD plus TDA times LDA is equal to 0. Okay. And we have LBC, LCD, LDA. Do we have this value? Okay, yes, we have LBC 0.2. It's 0.2. Okay, CD is 1.5, and DA is 0.3. And then we have, so finally we will have 0.2 TBC plus 1.5 TCD plus 0.3 TDA equal to 0. Okay. So we have another equation. But do we have TBA, TCD, and TDA? Do we have this value? Yeah, do we have this value? TBC, TCD, TDA, do we have this value? And yeah, this looks like we have another equation, but we have these two, but can we solve the TA and TB by these two equations? Yeah, okay, so and the next thing you have to also see, you have to also use the cut section method. Okay, the cut section method, what section we are going to cut, where we are going to cut. We are going to cut here and cut here and cut here. Okay, with these three sections. Okay, so the section, this is the section BC. Okay, the section BC. The section BC. The section BC. So in section BC, we have a torque at the end. Okay, we have this is C. This is a TB. Okay, and we don't know the TBC, so assume it counterclockwise. Okay. Okay, TB plus TBC, okay, must be equal to 0. So TBC is equal to minus TB. Okay, this is section BC, we cut section. So what is section CD? Section CD. I don't have any section. I don't have any space here. Okay, let me try to move here. Okay. For the section CD, section CD here, section CD. So for the section CD, so okay, section CD is here, section CD is here. So we have the TCD, and before section CD, we have here 800 Newton, and we have TB here. So in section CD, we have TB plus 800 plus TCD equal to 0. So TB plus TCD is equal to minus 80. Okay, so this is section CD. So finally, what's your section CA? Okay. Do we have any space? So no space. So okay, I just delete here. So if you want to take a note, just please rewind. So finally, I have to deal with section DA. Okay. Okay, section DA. Section DA. In the section DA. Section And in section DA, what do we have? Section DA, if I cut here, section DA. So I assume it's counterclockwise to your torque dA, TDA, and section dA we have 500 here and 800 here, and we have a TB. So TB plus 800 minus 500 plus TDA is equal to 0. So we will have TB plus TDA is equal to minus 300. Okay, so yeah, after all, can we solve the problem? Don't forget our goal. We want to find a TA and TB. We want to find a TA and TB. Do we have enough information right now? TA, TB. Okay, do we have enough information right now? Let's see. Okay, let's see. Okay, 0.2 TBC and 1.5 plus 1.5 TCD plus 0.3 TDA is equal to 0. And then we have the torsional balance in each section. Okay, how do we combine this information? Okay, the first of all, okay, we already know the TBC is equal TBC is equal to minus TB. Okay, so we start from this. Okay, we use start from this and erase this here. Okay. So from the cut section, we already know TBC is equal to minus TB. Okay, TBC is equal to minus TB. So we will have 0.2 minus TB. Okay, so TCD we already know TCD is equal to minus 118 minus TB. So it's 1.5. It's minus TB. And here minus TB over here, so a minus 800. And finally, we have TDA. What is TDA? TDA is equal to minus 300 and minus TB and equal to 0. Okay, see, we finally got this one equation. Okay, one unknown TB. So, and what is TB? What is TB? Okay, can we solve this? Can we solve this? Yeah, of course we can solve this. Okay, so let's solve this. Okay. Right. Sorry. Sorry. Okay, so it's minus 0.2, minus 1.5, and minus 0.3. So it's all minus, so 1.7. So it's 2.0. So it's minus 2 TB. Minus 2 TB, and minus 2 TB minus this is 1200, and this is minus 90 and equal to 0. So minus 2 TB is equal to 1290 Newton. Okay, so what is TB? TB is minus 645 Newton. And we already know TA plus TB is minus 300. So we can solve the TA. TA is just 345 Newton. Sorry, it's Newton times meter. Okay, sorry. This is Newton. This because this is torque. This is a torque. So it's Newton times meter. Sorry about that. And then I think we solved the problem. Okay. And the torque, this TA is positive. As initially we assume it's positive counterclockwise, so it's really counterclockwise. And we find the TB is minus. We initially assume it's counterclockwise, and we get a minus. That means it's clockwise. Okay. So be careful for your answer. Okay, so this is a very typical example of statically indeterminate torsional load member. Okay, just the same as the axial loading. If you use the balance equation, you cannot solve it. So you need to find another equation. In this book, it's called compatibility equation. I think it's called compatibility equation. And in this problem, competitivity equation is phi b angle twist between phi b and phi b related to phi a is 0 because this member is fixed in the wall. Okay, we apply the external torsion, but there's a reaction torsion to make the whole member doesn't have any angle twist. So this is 0. And then we can divide it divide it by this angle of twist by cut section method. We can calculate the angle twist in each section, and each section we use TL over GJ. Okay, and then we got this equation, and then we use this equation. We got this equation, and then we use the cut section method to get the torque balance in each section. And then we put everything in this equation, and then we got TB, and finally you have TB, we will have TA. Okay, this is very typical statically indeterminate problem in torsional member. Okay, very similar to axial loading. Okay, and it takes more time because it takes more time to do the calculation. Okay, so I hope you can uh do some practice of this type of problem because I don't think you have any experience on this. Okay, even me, I don't have any experience on this. Okay, so I just start the video here. Okay, see you in another video. Bye bye.